motion of rigid body, we have two types of motion. When the center of mass of the rigid body has the linear velocity, we can say that the rigid body is undergoing linear motion. The rigid body moves. The motion of the rigid body is characterized by two types of motion. One is linear motion, when the center of mass of the rigid body moves, the linear velocity of the center of mass is not equal to 0. When the center of mass moves with a non-zero linear velocity, or when the center of mass moves, the rigid body is said to be having linear motion. In linear motion of the rigid body, the center of mass must move. The center of mass must move. In other hand, in the angular motion, any straight line drawn inside the rigid body between any two points, if changes its angle of orientation with respect to any reference line, when theta or phi is a function of time, it may increase or it may decrease, then we can say that the body is undergoing an angular motion or rotation. So, rotational motion is characterized by angular velocity omega, which is defined as a vector and which is equal to the rate at which this angle of orientation of the straight line drawn inside the rigid body with respect to a fixed reference line changes with respect to time is called its angular velocity. So, angular velocity is defined as the rate of change of the angular position of the straight line with respect to a fixed reference line. From this, we need to define the angular acceleration. Before that, one thing I would like to tell you, this is a vector quantity because this is a vector quantity. D theta is a vector. D theta means very, very small angle or infinite small angle or elementary angle or differential angle. Is a vector quantity. Whereas finite angle, say theta, is a scalar quantity. Now I can one question. I can ask this question, why? Why a finite angle is a scalar quantity, whereas an infinite small angle is a vector quantity? For this, we have nice illustration. We have nice illustration. I am going to tell you now. Why does an infinite small angle or a very, very small angle we have as a vector, but a finite angle doesn't? Answer is because an infinite small angle obeys law of vector addition, because infinitely small or infinitely small, both are same thing, angle obeys law of vector addition. Say d theta 1 is a very small angle. When you add d theta 2 with d theta 1 will be equal to d theta 2 plus d theta 1. If you change the order also, they will be same. And this property is one of the special property of vector algebra. Vector A plus vector B must be equal to vector B plus vector A. Associative property. If you take a vector A, then you take a vector B, add them by putting the tail of one vector B at the head of the other vector A and joining the tail of the vector A to the head of the other vector B. This vector is the resultant vector of addition of these two vectors A and B. If you change the order of vector addition, you are adding B with A. Now you consider B first. You consider the vector B first. Then you add vector A with vector B. Are you not getting same vector? So diagrammatically you can understand that vector A plus vector B is equal to vector B plus vector A. This commutative law, it has to obey. But if you take finite angles, when we add them, theta 1 plus theta 2, you add, you are getting something. When you add them, changing the order, first you take theta 2, then theta 1. And you will find that these two are different quantities. That is some mathematical explanation. Physically also I am going to explain it. infinitely small angles obey the law of vector addition. But the finite angles, they do not. This is some sort of mathematical explanation. Now I will demonstrate by taking the example of a solid object. Look, this is the book. Even though it is flexible in some extent, I can consider this book as rigid. If I rotate this book in this way through 90 degree, this is the position you are getting. This was the initial position. This becomes the final position. So I am rotating this book through what angle? 90 degree. So theta 1 is 90 degree. Then I rotate the book with additional angle 90 degree. Coming back to the initial. This is the initial position. I rotate it like this through 90 and I rotate it through 90. So you are getting a position, this position after 2 rotations, completely physics. Let me retry. This is the initial position. I rotate it in this way. Then I rotate it in this way. You are getting this position. Now, I will do the same thing but in reverse order. What I did, I rotated in this way, then in this way. Now I do one thing. I rotate in this way now. Next I rotate in this way through same 90 degree. Are you getting same position of the object? This position after 2 rotation, previously after 2 rotation, you are getting different position. This position is totally different from this position, isn't it? So 2 different positions you are getting of the same rigid body by rotating through 2 finite angles, say 90 degree. However, you can take any finite angle and you are not getting the same position. When you are not getting same position, theta 1 plus theta 2, theta 1 is 90 degree, this is also 90 degree. This theta 2 90 degree, theta 1 also 90 degree. But when you treat them as vectors, suppose you treat all these angles as vector, rotate through 90 degree in this way, then in this way. You are getting this. This is the position, remember. Now, you reverse. First you rotated in this way, then in this way. Now you do one thing, you rotate in this way first, then in this way. Reverse the sense of rotation, or reverse the order of rotation, not sense actually, reverse the order of rotation. You are getting different position, exactly same position you cannot get. How? You can see that. You are getting a position, this position of the book totally different from the final position of the first experiment. So theta 1 plus theta 2 is not equal to theta 2 plus theta 1 when the theta is finite. So sum of 2 finite angles when you take in reverse order may not be equal. Therefore, these are not vector quantities. Finite angles finite angles are not vector quantities. The finite angles are not vector quantities. However, if you rotate the book through a small angle, you are getting this position. And when I reverse the experiment by rotating this book through small angles, approximately you are getting same position. First you rotate like this, little bit in this way, then in this way, you are getting this position. Then you come back, you rotate in this way, then in this way, approximately you are getting same position. So d theta 1 maybe 2 degree, 3 degree plus d theta 2, you are getting some position. And when you reverse the experiment or reverse the order of rotation and conduct the same experiment, then you are getting same position of the book. Therefore, d theta 1 vector plus d theta 2 plus d theta 1 is equal to d theta 1 plus d theta 2. Therefore, d theta is behaving as a vector quantity. Infinite small angle or infinitely small angle or elementary or differential angle are vectors, whereas the finite angles are not vector quantities or scalar quantities. This is the essence or the base or the basics of rotation of rigid body. So this is a nice illustration. Everybody should conduct this experiment. It's very easy to experiment. Once you understand this, then we can proceed to define the angular velocity, this elementary angle upon the time you are taking to rotate the object through a very small angle gives us another vector quantity is called angular velocity. Angular velocity is defined as the rate at which the angle of orientation of any straight line drawn inside the rigid body measured with respect to a fixed reference line is changing. That is what we define as angular velocity of the rigid body.